two-sample t-test. I have an example here that I slapped together. I already ran through it. I'm going to explain all the pieces there. The idea of a two-sample t-test is this. You have some population with a mean. You have another population with a mean, and you're trying to compare the two, and you're going to make comparisons using a hypothesis test. So you might argue that one population has a higher average than the other. We're going to try and show that. You might argue vice versa. The other population has a higher average than the other. We could try and show that. Or you could just say, I'm not really sure which one's bigger, which one's smaller. I just know they're not equal to each other. So that's what we're trying to do. So let's get to it. So a group of AP Stats students wanted to know if seniors' average weight was more than juniors' average weight. They collected a simple random sample of 15 seniors and found their average weight to be 172 pounds with a standard deviation of 9 pounds. They collected a simple random sample of 20 juniors and found that their average weight to be 165 pounds, standard deviation of 8 pounds. Both samples are roughly symmetric with no potential outliers. Test the students' claim at the 5% significance level. First thing I do when I start off pretty much all of these hypothesis testing and composite interval problems is I pull out all relevant information. So they told me I had a sample of 15 with an average of 172 and a standard deviation of 9. So N1 is 15, X bar 1 is 172, S1 is 9. They also told me about my average of juniors. So I have 20 juniors, that's going to be N2. The average of those juniors' weights, X bar 2, is 165. The standard deviation of those 20 juniors, S2, is 8. At the very end, they did talk about a significance level. 5% significance level means my alpha is 0.05. So then I'm going to run through phantoms, parameters, hypothesis, assumptions, name it, test statistic, attain a p-value, make a decision, state some context. So a lot of steps in this process to put together a full hypothesis testing problem, so let's get to it. Mu1 and Mu2, I defined what my parameters were. So I have two populations of interest here. Mu1, I care about that parameter of Mu1 is the mean weight of our senior students, so the average weight of all my seniors, and Mu2 is the mean weight of my juniors, my junior students, the average weight of all my juniors. My null hypothesis is always going to involve an equal sign, so we're going to assume the average weight of seniors is equal to the average weight of juniors. We're going to assume this is true all the way throughout the problem until it's not, okay, until we can maybe prove the alternative. So we assume the null until we get to the very, very end, and then we make a comment on that. We argued Mu1 is greater than Mu2. We believe, and what we're trying to prove is the average weight of seniors is more or greater than the juniors. Our assumptions, very, very important. We need our assumptions. If we don't have them, problem falls apart. Can't exactly do it, okay? So we need our assumptions, otherwise everything crumbles from here. So that's the next logical thing. 3 things I'm going to check is independence, 10%, and n is greater than or equal to 30. Independence, both samples were randomly selected. In fact, they were simple random samples. That's going to help me with independence. Next thing, 10%. Each sample is less than 10% of the population. So we're hoping these 50 seniors that it's less than 10% of all seniors in the school, which would be 150. Juniors, there's 20. We're hoping that's less than 10% of all juniors in this school. So that 10% is also helping with independence. We're making sure our samples aren't too big. Finally, we want to make sure our sample isn't too small through n is greater than or equal to 30. So we hope both sample sizes are greater than or equal to 30. The samples of 15 and 20, those are not big enough, okay? They're not greater than or equal to 30, so we have to do more. What I would love to do is take each sample, take the raw data, get a box plot out of it or some sort of graphical display, and I want to check and make sure things are roughly symmetric with no potential outliers. So I'd like to take a look at both of these samples and see what they look like. But there is some information in this problem. It says both samples are roughly symmetric with no potential outliers. So it looks like that work was done for us. So I note it here. I said, but told samples are roughly symmetric with no potential outliers. So I know my sample size, even though it's not greater than or bigger than 30, since we are roughly symmetric with no potential outliers, we're good there. So we have all 3 of our assumptions met. That means we can move forward with the problem. So we are doing a 2-sample t-test. I did run this in my calculator. I went to stat, I went over to calc, and I looked for a 2-sample t-test. I entered in all of my relevant information, my alternative hypothesis, and I ran it, okay? in the formula here, so it's t equals x bar 1 minus x bar 2. So got those from up above. Minus mu1 minus mu2. Well, we know mu1 and mu2 are equal to each other. We do not have the numerical values, but if you're going to try to do mu1 minus mu2 here, if they're the same number, well, they should subtract to 0. We're going to divide by the square root of s1 squared divided by n1 plus s2 squared divided by n2. So basically taking our variances, divide by the sample size, add them together, square root, that's going to give us our t-score of 2.39. Now, again, anytime you're dealing with t, you are going to need a mention of degrees of freedom. My calculator tells me the degrees of freedom is 28.21. So that's my test statistic. I need to obtain a p-value and make a decision. So I drew a t-distribution here. It's centered at 0, has a standard deviation at 1. I got a t-score of 2.39, and I want the area above that. So the proportion of t-scores that is greater than 2.39 is 0.012. I got that all from the calculator. This is my p-value. My p-value is 0.012. That's going to help me with making a decision here. Now, my calculator did send me this information here. I just wrote it all down. If you wanted to get a p-value by a chart, what you would have to do is find your degrees of freedom, which we were 28. What was it? 28.21. So we're between 28 and 29. And you would look for the closest thing to your t-score, which is 2.39, which that would be between these two t-stars here. It's hard to see on the screen, but that's 2.15 and 2.462. So my t-score is in between these two. So my p-value must be between 0.01 and 0.02, which, hey, check it out, it is. So that's how you can get there with a t-table. Go your degrees of freedom, find your t-score you got, go up, and you're going to figure out some p-values. So I got a p-value of 0.012. Our alpha, our significance level was 5%. So anything less than 5%, we're going to reject. Anything bigger than 5%, you would fail to reject. So with a p-value of 0.012 and my alpha of 0.05, we reject the null hypothesis. Our p-value of 0.012 is less than our alpha equals 0.05 level. So since we're below that 5% threshold, we are going to reject. So I'm commenting on my null hypothesis first, now my alternative. There is sufficient evidence. So if we're saying no to the null, that means we brought enough to the table for the alternative. Sufficient evidence to say the average weight of seniors is more than the juniors. A lot of pieces there for that 2-sample t-test. Take some time, make sure you get all the fine details correct. But again, that is a 2-sample t-test.